Hi everybody, this is Andy Randano, co-founder of Alef Omega, the company that created Alef, which is the math program that you see in front of you. So what I want to do today is derive the solutions to the quadratic equation. So this is a somewhat difficult calculation. It's more difficult than most students will encounter in Algebra 1. They'll certainly see the quadratic equation, but they're usually not asked to derive the generic solution to it. But I wanted to do it for two reasons. First of all, I wanted to demonstrate that Alef is an incredibly powerful tool for doing interactive math. Secondly, I wanted to show that Alef can be used effectively as a presentation tool. So let's jump into it. Here we have the quadratic equation, somewhat infamous quadratic equation. Ax squared plus bx plus c is equal to 0. So our task is to find the set of x's such that this equation is true. And it turns out there's two of them. We're going to derive both of them here. So to do this, let me first put this in a slightly more convenient form. Let me just divide by a. And you'll see why that's a little bit more convenient in a second. Okay, so let's take that as our starting equation. Okay, now the strategy I'm going to take here is I want to show that the quadratic equation, the equation above, can be put in the following form. I want it to take the form x minus x sub 1 times x minus x sub 2 is equal to 0. Okay. Now why do I want to do that? Well, of course, because the bottom equation has very simple solutions. If x is equal to x1 or x2, the left-hand side is 0, so the equation is solved. Okay. So to show that the top equation can be put in the form of the bottom equation, let's set them equal to each other. Okay. Now let's manipulate the left-hand side a little bit. We get an x squared term, which is great because that's what we needed. Distribute the minus sign. Okay. Now let's combine the x's. All right, and we're almost done. Okay. Now we see the left-hand side and the right-hand side both have the similar form. Just remember that x1 and x2, those are both constants. So this constant in front of the x is just, well, it's just a fancy constant. All right? But in order for this equation to be true, well, let's cancel out the x squareds. In order for this equation to be true for any value of x, we have some very strong conditions on x1 and x2. In particular, the coefficient in front of the x on the left-hand side has to be equal to the coefficient in front of the x on the right-hand side. More specifically, b over a has to be equal to the coefficient on the left-hand side, which is negative x1 plus x2. Okay. Now the same thing holds for the constant term. We have to have constant term on the right-hand side is c over a. That has to be equal to the constant term on the left-hand side, which is x1 times x2. Okay, so now let me get rid of this equation. We're not going to need it anymore. All right. So now we have a system of equations that we can potentially solve. So to see what we're doing, let me clean this up a little bit. Pull the negative sign over here. Okay. So we have two equations and two unknowns. The two unknowns are x1 and x2, two equations with constants on the right-hand side. So we're trying to solve for x1 and x2 in terms of a, b, and c. Okay. So to solve this, it's a little bit tricky. There's a trick that we have to use. So here's what I'm going to do. I'm going to make the ansatz that x1 can be written in the form alpha plus beta, where alpha and beta are just numbers that are yet to be determined. And x2 can be written in the form alpha minus beta. Okay, now so far I haven't done anything. I've just written x1 and x2 in a different form, but this will be a very convenient form. And the reason why I wrote them like this is if we notice this equation over here at the top involves x1 plus x2. So if we substitute x1 is equal to alpha plus beta and x2 is equal to alpha minus beta, the plus beta and the minus beta cancel out, so we can solve for alpha, which is great. Okay, so we've solved for alpha. Now let's see if we can use the bottom equation and solve for beta. All right, so combine these two factors. All right, get an alpha squared, get a beta squared over here. And now notice these two terms in the middle end up canceling out. All right, so much cleaner now. We can go through and solve for beta. All right, so now we've got beta squared in terms of alpha. We know what alpha is, so let's just substitute that in. Okay. And let's combine these two factors. A lot of algebra here, but it's all straightforward. Okay, so now we can go through and take the square root. We've got beta exactly, and to get it in a more familiar form, what I'm going to do here, zoom in a little bit, is distribute the factor of 1/2. Okay. Almost done. Okay, great. Now we have both alpha and beta in terms of A, B, and C. Okay. Now let's take those, what we just derived, plug those back into our ansatz, our guess for what x1 and x2 look like. Okay. And let's combine factors here. And there we go. We're done. Okay. We solved the quadratic equation. Quadratic equation, one at the top, has two solutions. x1 is equal to this. x2 is equal to that. Now, the solutions are usually written as negative b plus or minus square root of b squared minus 4ac over 2a. So we've just written it in a slightly different form, but still the same solutions. Okay, so we've solved the quadratic equation. Thanks for watching.